Hello and welcome to Logarithmic Functions and their Graphs. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1508 at UTEP. It's called Pre-Calculus. We're using Larson's 10th edition of the Pre-Calculus text, Chapter 3, Exponential and Logarithmic Functions. This lecture is for 3.2, Logarithmic Functions and their Graphs. So let's start with a definition. For x greater than 0, a greater than 0, and a not equal to 1, y equals log base a of x if and only if a to the y equals x. If we call this an f of x instead of a y, it's called a logarithmic function with base a. All a logarithm is an exponent. Now, where does this come from? Keep in mind that exponential functions are one-to-one. So if I have some exponential function, I know it's one-to-one, I know it has an inverse. If it has an inverse, in order to find the inverse, I'm going to switch the roles of x and y, because that's all an inverse does. And then I ask myself, alright, how do I solve for y? That's a y, not a 4. Let's see if I can make that a little better for you. That's a horrible eraser. There we go. X equals a to the y. Well, we had no tools to get the y out of the exponent. And so, defined literally, y is the exponent to which you raise a. In order to get x. But that's way too much for a mathematician to continue writing down, so we wrote it in notation. Y is the exponent to which you raise a, log, with a little a. Because all an exponent is, all a logarithm is an exponent in order to get x. And so literally, in writing down what do we want this logarithm to be, we were able to find and define our logarithm. So let's write them in exponential form. If I have log base 7 of 343 equals 3, I know first of all that the base 7 of log is going to have an exponential of base 7. I know secondly, the log is equal to the exponent, so 3 is my exponent. And what does this say? This says that 3 is the power. 3 is the power. You put on 7 in order to get, so equals 343. Let's try some more. Log base 16 of 8 equals 3/4. The base of the log is 16. The base of the exponential is 16. The log is equal to the exponent, so 3/4 is the exponent. 16 to the 3/4 power equals 8. Anytime a base is not written, this is going to be a special logarithm. If I just have log of x, that is log base 10 of x. This is called the common logarithm because, well, most of us have 10 fingers, 10 toes. We have a base 10 counting system because of those fingers and toes, and so it's commonly used. So anytime you have a base of 10, we just don't write it. So this is log base 10 of 1 over 1,000 equals -3. Base of the log is 10. Base of the exponential is 10. The log is the exponent, so -3 is the exponent. 10 to the -3 equals 1 over 1,000. Log base 8 of 4 equals 2/3. The base is 8. The exponent, the log, is 2/3. 8 to the 2/3 equals 4. So give it a shot. Hit pause for a minute. And when you come back, check your answer against mine. The base of the log is 5, so the base of the exponential is 5. The log is equal to the exponent, so -2 is the exponent. And 5 to the -2 is 1 over 25. Good job. So now let's look at some examples and rewrite them in logarithmic form. It's a fact, 13 squared equals 169. The base of the exponential is 13, So the base of the logarithm is 13. Remember, 2 is the power to which I raise 13 in order to get 169. I like writing these in the other order. I don't know why I typed them as I did, but for number 2, 3/2 is the power, that's all a log is an exponent, to which I raise 9 in order to get 27, and we'll frequently use a parentheses. -3 is the power to which I raise 4 in order to get 1/27. We're going to pretend that that looks like a 2. Here's some properties of logarithms. Log base a of 1 equals 0 because, what? Well, the base of the log is a, the base of the exponential is a. Log equals the power, so 0 is the power. What is a to the 0? Well, as long as a is not 0, that's equal to 1. And we know, through the definition, that a can't be 0. Think about what this says. What power, that's all a log is, do I put on a to get a? Well, it's the first power, because a to the first equals a. Alright, this is another one. What power do I put on a to get a to the x? Well, I just put on the x power. Also, log base a of x is defined to be the power that I put on a in order to get x. So we think of these as the definition, and this shows directly the inverse relationship between an exponential and logarithm of the same base. We have a one-to-one property of logarithms that says log base a of x equals log base a of y. If that holds, then x must equal y. There's another one, very similar, that says if b to the x equals b to the y. Let's write this correctly. Then x must equal y also. This is a one-to-one property of exponents. We'll be using that in the next section. So let's simplify. Log base 3.2 of 1. So I want to know what's the exponent that I put on 3.2 in order to get 1. Property 1 says this is equal to 0 because anything other than 0 raised to the 0 power is 1. Alright, so log base 9 of 15 is the power to which I raise 9 in order to get 15. Alright, so this is equal to 15. That's not a logarithm. Sorry, I was distracted. Let's just cancel that word out. Simplify some more. Log base pi of pi. What power do I put on pi to get pi? Well, that power is 1, so this logarithm is equal to 1. What power do I put on 11 to get 11 to the 7th? Well, this is 7. Think carefully. What power do I put on 11 to get 11 to the 7th power? Well, it's the 7th power, so the answer is 7. Let's look at some facts. The graph of a logarithmic function is the inverse of the graph of the exponential function of the same base. We talked about that. So all an inverse does is switch x and y. We know the y-intercept of an exponential function is 0, 1. So the x-intercept, right, switches x and y's, of the logarithmic function must be 1, 0. The domain of all exponentials is all real numbers. So this is the range of the logarithms. The range of exponentials is y greater than 0, and so the domain of logarithms must be x is greater than 0. So as long as you know information about one, say exponentials, you also know corresponding information about the logarithmic functions. If we look at the graphs, exponentials in blue, logarithms in green, for an a value greater than 1, we know our exponential function is increasing with y-intercept at 0, 1. Our logarithmic graph, right, axis of symmetry, y equals x, a mirror reflection. This is going to be my graph of y equals log base a of x, and now it's going to have an x-intercept of 1, 0, still increasing. For a between 0 and 1, my graph of the exponential function is decreasing. If I have an axis of symmetry here at y equals x, this is a little hard to see, but if you flip it over, if you fold across this line, which I do not recommend you doing with your phone or other electronic device, but imagine, if you will, folding across this line, this green portion would lay on top of the blue, this blue portion would lay on top of the green. They are reflections. X-intercept, Y-intercept. They're both decreasing as we read from left to right. Domains of both logarithms, positive values. The range of both logarithms, all real numbers. Reverse that, and we have the domain and range of exponential functions. Alright, so we talked a little bit about the common logarithm, but let's have a formal definition now. The function defined by f of x equals log base e of x, special notation, ln of x, with x values greater than 0 is called the natural logarithmic function. And I want to just throw out there here, make sure this is big enough for you to see it, logarithmic function. That's an L. I know it looks like an I, but come on. It's a logarithm, so make sure that's an ln of x. The function defined by f of x equals log base 10 of x, which is log of x, we just don't write the 10. It's called the common logarithmic function. The word logarithmic is being shortened for our notation. It's an L, right? It's an L, not an I. So please, if you're writing this on paper, it drives me nuts when people write in of x, because that's nothing. That's in x. That's half, almost 3/4 of a band from the 80s. This is an L. Alright, so let's use the one-to-one property to solve some equations. Here we have log base 5 of x plus 1 equals log base 5 of 6. Well, the one-to-one property says log base 5 of one thing is equal to log base 5 of something else. Since it's the same base, it must be that x plus 1 equals 6. If x plus 1 equals 6, I subtract 1 from both sides, and x must be 5. Do not overthink this. If the natural log of x squared minus x equals the natural log of 6, they're both natural logs. So I can just solve x squared minus x equals 6. Anytime I'm trying to solve a quadratic, I'll get it equal to 0. Once I get it equal to 0, I'm going to factor. I'm going to check and make sure I factor it correctly. I'm going to set each factor equal to 0. It looks like the other part of my equal sign ran away. It'll come back eventually. It is probably not today. X minus 3 equals 0, or x plus 2 equals 0. So x equals 3, or x equals negative 2. Now remember, we said the domain of a logarithm is x values greater than 0. But I just got an answer of x equals negative 2. We must consider each function separately. If I put negative 2 in here, for x, negative 2 squared is 4. 4 minus a negative 2 makes 6. So the total argument of the function is still positive. So an x value of negative 2 does not make the inside, the argument, of the logarithm negative. So it's just fine for an answer. Alright, word problems. Logarithms used in word problems as well. Students in a mathematics class were given an exam and then retested monthly with an equivalent exam. Yes, this is what summer nightmares are made of. The average scores for the class are given by the human memory model, f of t equals 80 minus 17 log of t plus 1. And these are for t values between 0 and 12, where t is the time in months. So we're going to do several things with this. We're going to sketch a basic graph of the function, and you better believe I'm going to use Desmos for that and make it look pretty. We're going to see what the average score was on the original exam, and then see what the score was several months later. So first, a basic sketch. Again, Desmos makes it so easy to graph. They don't pay me to say this. If they wanted to send me some money, I would take it. But it's fantastic for being able to view what you need to see. Here's a logarithm. Because of the negative out in front, it was reflected across the x-axis. Sorry about that, a little hesitation. We have it stretched, we have it shifted up, we have it shifted left. A lot of things going on with our basic log graph. And when we graph it, alright, I can see what's going on. Notice after 1 month, the scores are about 75. After 4 months, they're a little less than 70. After 9 months, a little above 60, maybe 62. After 12 months, the scores are getting close to 60. It looks like here at time 0, the original scores were 80 on the exam. No coincidence, just saying. Let's take a look at the actual questions. What was the average score on the original exam? Well, when t equals 0, I'm putting 0 in for t. 0 plus 1 is 1. Log base 10 of 1 equals what? Well, what power do I put on 10 in order to get 1? The power, the logarithm, is 0. So this is 80 minus 17 times 0, which is 80. The average on the original exam was an 80. What was the average score after 4 months? After 4 months, I'm putting 4 in for t. 4 plus 1 is 5. I type this into my calculator exactly like this using the LOG button. I must use the LOG button, not the LN button, because they are different functions, different bases. 80 minus 17 log of 5 in my calculator, that's about 68.1. And 6 months after that, so after month 10, I'll be looking at 80 minus 17 log of 10 plus 1, so log of 11, which is about a 62.3 on the exam. After 10 months, scores have dropped almost 20 points. Let's see if you could do better at remembering that. Make sure you learn it backwards and forwards. Thanks for listening.